as we took the measurement, there is a light already in the room which is also throwing some light onto the surface. All of these things are happening. While she's reading, her shadow might be cast on the robot. Are you following? So we want to look at how to calibrate our robot or our light sensor. How do we calibrate this? First of all, we are going to look at a principle that we all know. We have all seen this before. We've all seen this equation before. We've all seen this equation before. It's what? The equation of what? A straight line. Now, if this is the equation of a straight line, what does it say? It means if I have any object or any sensor or any signal which is linear, then if I know the equation of this line, I can predict the behavior of that signal. I get it. So we are going to say that according to physics, or what we want to achieve is that we want the black surface to give us 0% reflection and the white surface to give us what? 100% reflection. However, if I take this to be my light sensor axis, and I take this to be my, let's say, ideal values, or what I want, what I expect, I follow it, then I can say that for my expectation of 100, when I measured, what did I get? Let's take the average of these three numbers. What do we get for the average? Average? You have to calculate this. Maybe you can calculate it. 71? Is it 78.5? No. Average, add this and divide by 3.
What should the calculate it?
Oh, I think okay, how was it? 79.1. How will you okay, how was it? Your brain is like a muscle. You don't use it, you will lose it. Okay, so this is the average value for white, and what would be the average value for black? 10.7. So ideally, this is how our robot is seeing a white, or the reflection is getting for a white, and the reflection is getting for what? For a black. So I can plot this, I can plot my light sensor's behavior against my expected behavior and say that when my light sensor, or when I expected 100, my light sensor recorded what? 79.133. And that gives me what? 1 point here. I follow. When I expected 0 reflection, what did my light sensor record? 10.7. I follow. And where would that point be? X axis, Y axis. 10.70. Where will it be? Yeah. On the what? On the 10.7. I follow. So this gives me what? A line. And that line will meet what? My Y axis somewhere. So you can see whatever we are in the classroom is coming back. Now, if I know the equation of this line, which I can quickly get by doing what? Finding what? My gradient. I follow. So my M, which is equal to what? Change in Y over what? Change in X will be calculated as what? If I take this point as 0.79.33, 100, and this point becomes what? 10.7, 0. Change in Y can be what? 100 minus 0 over what? So what? Minus what? So what do I get? 100 over what?
69 points. 68.
You have to calculate this quickly.
Those with the calculators.
67.1.
63.
Okay, so what do we get? 1 point. 1 point what?
1.47.
1.47. Okay. Now I can then substitute my n value. Pick any of the points. I prefer to choose this point. I follow it. And so if I'm dealing with this point, then I can say on this point y is what? 0. 0 should be equal to what? My m, which is 1.147 times what? The x value at that point is what? 10.7 plus what? C. So C should be equal to what? This cross I have minus what? So C equals what? 0 minus. Let's multiply this. 15.1. 72. Okay. So I have C to be equal to what? Minus 15.72. So this is my C and this is what? My M. Which means the equation of this line is y equals what? 1.47 times what? My line sensor. Remember, this is the line sensor axis. X is the line sensor axis. Minus what? 15.72. What this means is that if I record 79.33 and it goes through this equation, it will translate y to what? 100. And when I record 10.7 and it goes to through that equation, it will translate the value to what? To 0. So I have calibrated the behavior of the light sensor such that 10.7 has become what? 0 and what? 79.33 has become what? 100. And any value within will have a corresponding value. I follow it. So this is how we calibrate our light sensor. Now that we have this equation, the task is to program this equation into our robot and say that we know your light sensor is not perfect, but we have created an equation for you. When you read your light sensor value, pass it through this equation and use the results or the y value you get from that equation as your recorded value. It's just like wearing glasses. Before you watch, whatever you are watching goes through the glasses before it goes through what? To your eye. I follow. And the glasses will do the correction. Are we there? Good. So let's try to build this simple equation. Let's try to build this simple equation. So I start my environment. Let's build it together first. Later you have a chance to try it out. So there is the Lego Mindstorm environment used for programming these little machines. I start my software, and all I can say is I create a new project. So file, new project, and then I create a program within the project. This is how it will look like. At the top, okay, so at the top we have project, and within it we have program. The project is the entire folder, and the programs are the instructions you have written. I follow it. So we have a brain, and within our brain we have a lot of different instructions. There's an instruction for dancing. There's an instruction for what? Eating. There's an instruction for some other thing. So we are going to create this together. Okay. So the first thing is that we want to build the equation y equals 1.47 times what? The light sensor reading. I follow you. Minus 15.172. So I need to multiply, which means whatever the light sensor is seeing, or whatever value the light sensor is recording, must be multiplied by what? 1.47. And then 15.7 to subtract it from it to achieve what? The original value, or the correct value that we need, or the calibrated value. So let's do it this way. Below here we have the programming blocks. they've been grouped into sections. The first section gives us all the actuators, that is the motors and all what we have. The second section gives us what we call the flow control. The third one gives us the sensors, all the sensors that we can deal with. The fourth one gives us the chance to perform computation, mathematical computations. So that is the data operations. This allows us to do some advanced stuff like Bluetooth connections and the rest. And then the last block allows you to create your own block, a block that does not exist. An instruction that does not exist. You can create your own instruction. So I'll say that here, this equation contains what? A constant value, 1.47. So under my data operations, I have a block for a variable and I have a block for what? A constant. So I can say I need a constant. I just pick that, drop it, and the value for that constant is what? 1.47. That value must be multiplied with what? The light sensor reading. So I'll say that here you don't pick a reading because the robot will be moving, and as it moves, he will be getting his readings from what? The surface that he's moving on. So I'll say whatever the light sensor. So I pick here. I'm going to choose a color sensor, and I will explain why. Previously, on Game of Thrones, previously we had. So previously we had the NXT robot. The NXT robot came with a separate color sensor and light sensor. But the new robot, that's the EV3, comes with one single sensor that can perform the function of color detection and light detection. So in the software, you just see a color sensor, but you can use it as a light sensor as well. So I'll say I need a color sensor, but my color sensor can be used in multiple ways. I can use it to measure color. I can also use it to measure what? Reflected light intensity. So I'll say using this color sensor, I will want the color sensor to measure how much reflection is coming from a surface. I follow. These two values will have to be what? Multiplied. So which of the blocks do I need? Under data operations, I have what? The math block. I can pick the math block and say, I have the math block, but I want to use it to do what? To perform multiplication. What do I want to multiply? Multiplication takes what? Two variables, right? Good. I can also say, so I'll do this, I'll say multiply the light sensor reading by what? This constant value. The result will come out of what? Of this block. But this result, what do I want to do? I want to subtract what? 15.72 out of it. So I need another constant. So I'll go back to my constant and say, I could have gone this way and say I have another math block to say the result coming out of this. Remember, subtraction is not commutative. I want to subtract what from it? A constant which is what? 15.72. So I could do this. And then the final result that comes out of this is what? The Y value, or the calibrated light sensor reading. Which means my robot will not be using the wrong values it is recording because of the influence of light in the environment, somebody's shadow, and all of those things. It is going to take the value, alright, but it will do it correction before it applies the value to make thinking. Are we there? Are we there? Yes, good. I could have also decided not to have this block here at all and say I will change the operation here to advanced. And the advanced operation allows me to have multiple input and type in my equation. So I could say this is coming to A, that is coming to B. I will connect this to C and say multiply. I'll say the operation I want you to perform here is to multiply input A times what? Input B, and then subtract what? Input C from that. Where input A is what? Light sensor, input B is my constant, and input C is what? The other constant. So I could have done this as well. Either way is correct. Are we there? Good. So this becomes our calibrated light sensor reading. So we want to say the robot is supposed to use this reading to take a decision. The task is that you want the robot to follow this black line on a white mat. But this robot has just one sensor, just one light sensor. So the task is, if you were a human being, that's what I always say, if you were a human being, and this is how you look like, and you have this ability, how are you going to use it to follow this line? Because you do learning, you wouldn't have found a problem. You can clearly be on this and say, oh, okay, I'm going to my left, I'm going to my right, or I'm going straight, I follow it. So what we are going to say is that I could say, or okay, let me ask, how would you use this? Or how can we use this value to teach this robot how to navigate this mat? Anybody to try? Robert, read the last one.
Because of how narrow the black is, we might be having reflection from the white. So I would rather program it to pick the I don't know how to put it. I'd rather program it to pick not necessarily the black, but the white instead of the black.
Which of the white?
The white around the black.
No, there are two whites around the black. If I take this, there is a white to my left, and there's a white to my left, and there's a white to my right. So the whole thing is that the robot should know that if I am on the white, it means I should go towards the black. I follow. So if I say, okay, you are on the white, what if it goes into this white? We could program this robot and say, be on this white. Now the disaster will be this. If you are on the white to the left, it means in the robot mind, your mind is that the black is towards my right. Anytime I see white, it means I should go into my right. If it mistakenly gets into this white, the thinking is going to be that, oh, I've gone into the white. The black is what? On my right. And it's going to turn in the other direction. So your mindset, which you can distinguish between white on my left and white on my right, is not same for the robot. I follow. All the robot knows that white. When I see white, what should I do? If you say when you see white, turn to the left, it means whenever it sees white, it will turn to the left. And you cannot instruct the robot, when you see white, turn to the left, when you see white, turn to the right. Then you get the robot confused. Because when he sees white, there are ambiguous decisions to take. I follow. How can it know that this white is the one on the right and the one on the left? So with one light sensor, the best we can do is to say, stay in between the white and the black. Stay in between the white and the black. When you are getting too much into the black, get to the right, to the left. When you are getting too much into the white, get to the right. So that he knows that when I'm going here, I should come. When I'm going here, I should come. He does not eat into the other one. The moment he gets into this white, he's going to get confused. Are we following? Now, if I should put this robot in the middle of this, with my calibrated value, knowing that the white is giving me 100% reflection, the black is giving me 0% reflection. If I put the robot halfway on white and black, what percentage of reflection are we expecting? How much? 50. Exactly. So the black is going to absorb 50% of the light, and the white is going to reflect what? 50% of the light. Are you getting it? That gives us a decision boundary. Human beings can only take decisions when they have a boundary. What is the pass mark? 60. Then I can say you have passed or you have failed. But if a pass mark has not been determined, there is no way I can tell whether you have what? Passed or have failed. Are we there? So our decision boundary is now what? 50. So we are going to program this robot to take a decision based on the light sensor reading that has been calibrated. The question? Okay.
So does it mean that when you put the robot anywhere apart from where the black is, they cannot find its way to the black spot?
Okay. So this is what robots do. They don't have a brain of their own. So they will respond based on what you program them to be. So if your decision only centered around these values, every behavior you see is as a result of what you programmed. So you cannot predict the robot behavior, you cannot do, all you can say is that it will respond to how it has been programmed. So you just let's see how it will behave if you try, and then you try to explain it based on nothing but what you programmed. So we will say that after you've calibrated this value, remember, the light sensors are connected to port 1, 2, 3, and 4. The one I have here is on port 1, which means in this program, I will have to make sure that the light sensor I'm using is what? On port 1. So I say after you have measured your light sensor value, multiply it by 1.4, subtracted 15.72 out of it, the result is going to be used to take a decision. There is a block here labeled the switch block. The switch behaves just like the switch we have on our wall. It is either on or what? Off. It is used to take a decision based on values. I follow you. So we are going to say there is a decision to be taken. And this decision we are going to take depends on a value coming from the light sensor. If the light sensor value is above 50, what it means is that we know we are in the white, or we are getting too much into the white. If it is below 50, we know we are getting too much where? Into the black. So it means the value that is coming out of here, we must compare. So I go back to my data operations and say, we want to compare the value coming out of this equation. We want to check if that value is greater than. So if this value is greater than 50, the result we get from this comparison is either a true or what? A false. I follow you. So we say our decision with the switch block will be based on a logic. I follow you. So we receive the logic from this comparison and say the logic that comes out of here should be used to perform one of two actions. The switch block can either be true or false. So it says it is going to be a logic, and this logic will drive us to either true or what? False. So if it is true, what do we do? And if it is false, what do we do? So there is a thinking that we are programming into our robot. If it is true that the value from the light sensor is more than the threshold, then we want to take a decision of, it means I am here. I'm more into the white, so I should do what? I should turn towards what? The black. How do I turn? I'll say stop one of the wheels and move the other. It's just like a vehicle. I follow you. So if I should stop this wheel and move this wheel, what is going to happen? I'm going to move towards what? The black. So I will say this my wheel is connected to motor D, and that is connected to motor A. So I'll say if this is the case, if you are too much in the white, these are the motors. The motors we have here are what we call the large motors. There are other motors, medium-sized motors, but these are the large motors. So I would say I have a large motor connected to port number D. If the value is more than 50, then that motor should be turned off. I follow. That motor should stop. And I have another motor on port labeled A. I follow it. If that is the case, that motor should be turned on. So I am turning off. If it is this way, I'm turning off this motor and I'm turning on this motor. What will that do? That motor will move and bring me back on track. I follow it. The other situation is when I am getting too much into the black, the value will begin to fall below 50. And then quickly the decision will be taken that if the value is falling below 50, you get the fall. What do I do? This time I stop motor A rather and do what? And move one motor B, and it will straighten me. I will follow you. Good. So let's take that decision as well. So we say if that is the case, then this time motor D rather should be on, and then motor labeled A should be off. Are we there? So we have taking our decision, So virtually we have gone through what we started with, practically by saying that the robot has a sensor. The sensors are connected to a brain, which we call an intelligent brain. Sensor receives values. It transmits the values to the intelligent brain, or the brain, which is a computer. The brain processes that information, but the brain can only process based on what you have programmed it to do. Then it sends signals to actuators or motors. So here, what do we have? What we have here is our sensor taking information. After it takes information, we went one step ahead to say that information will have to be refined because we are in an imperfect world. How do we refine it? We use the equation of a straight line to calibrate that sensor because we had taken values. It's just like you go to the optician. First of all, you have to do that eye check, S, T, and then he looks at that and says, no, I need to fix you. Then he goes to do some calculations, brings you a glass with some focal length, and then there you go. So here we also took readings, checked the readings, they were not perfect. So we said, what can we do to perfect it? We took the equation of a straight line. We plot our behavior against the ideal behavior, and we find the correction that has to be applied to our values. And we program that by saying that is the equation, mx plus c. So our m1.4 times the light sensor reading, and then we subtract our constant from it. The result is what we feed to the brain. That result is being used to take a decision. What was the decision? We are taking a boundary of 50 because values above 50 are more towards the white and values below 50 are more towards the black. The decision is that we either move to the left or we move to the right. So that decision goes to our actuators or the motors. So we are going to test our first program, and then we move on to some other interesting stuff. Before I test the program, I'll do one last thing. There is a block here labeled the loop. The loop is used to repeat actions. So I pick a loop and say that this is my instruction I have written. I want my robot to use that instruction over and over again. What that allows me to do is, the robot can say, okay, for the entire of my life, this is my thinking. So I'm able to use that throughout. I don't have to program from here to here, from here to here, from here to here, from here to here. I put the whole thing in the loop. So let's select everything. Just when I was about testing. So I select everything, and then we drag it into our loop. And finally, what we have to do lastly is to connect our robot to the computer and download the instruction. The instruction we have written will have to be downloaded onto the robot.
Okay. I don't know how the system works, but if the robot is already, I assume that the robot is already moving, right? And then range, this is deviating. If it's deviating, I want to bring it back. If it's already moving, do we have to still switch on the motor? Don't we have to stop only one because this one is already 10? We have to still put it on to 10. See, both ties, the ties they are both on and they are running. And then we reach, we deviate. So if we deviate and want to come back, don't we have to stop only one time? We stop one, this one is already moving, and then
so the ties are not already moving.
They are not already moving.
You see, that's why we say that the robot does not do anything except what you have asked it to do.
But it's moving.
No. So
you put it there,
it is not moving.
It's not moving.
Listen, the thing is this. This is the instruction you have written. The robot has no default behavior. Anything that can do move on its own does not need to be programmed. I follow. So if in this program we wrote that the robot should be moving, then the robot will be moving. But the instruction we have written here does not contain moving. It only contains moving where? Here. And the movement it contains is based on a decision. So the robot only moves based on its light sensor. And how is the moving done? The moving that we instructed is at all points, one is stopping and the other is moving. I follow. So it is not the case that we write instructions while the robot is constantly moving and applying. That is when we write it. I follow you. So if we have not written it, it will not, that is not the case. But we'll write instructions where we keep the robot constantly moving and we apply the corrections. I follow you. But for the instruction we have written, this one, the only move part we have here are this. And those moves are with respect to what? The sensor values. So we'll test it quickly and then we'll see how that behaves. So once you connect your robot to, you can download the instructions onto the robot. You can download and run. Let me just download and run. So I can see one wheel is moving, the other is stationed. Why do you think that is the case? Because this sensor is flowing light. The light is not bound over anything, so nothing is coming back. So the percentage of reflection is getting is almost 0. So the instruction says when it is less than 0, do what? See, I bring it into the projector and it's trying to respond. Because now the projector is throwing light into it. I follow it. But I bring it here and 0. 0 says stop D and move what? A. If I should bring it very close to the projector, see, it's trying to pick some signals. If I should show it to this white surface, now this one has started moving and that one has stopped. I follow it. So now let's try to put it on the mask where we have white and black and see how it behaves. So when he's going into the white, he has instruction that stop this one and move that one. When he's going into the black, he has instruction that stop this one and move that one. And we have a look. The moment he gets into the wrong part of the white, like we said, he's going to get lost. If I should put him here, he will be looking for the black on his what? On his left, which he will not find. So he keeps going in what? In circle until he finds the black. Then he tries to respond. I follow. So this is the instruction we group. And if he gets this, he will still try his way around. Because you put it in the loop, it is going to keep that behavior up for as long as the track exists. Are we there? However, this is the simplest way of navigating, and it's not very perfect. So this is what we are going to do. Like what Engineer Berman asked. Do we have to always be stopping one and moving the other? Or let's start from here. With what we just did, this approach is called the drunken sailor. So I'll pop up this slide. We have gone through our calibration. We have built this block. And then what we have done is a single line follow. So what we have done